might see, and actually it has more to do with last week than it had to do with this week. So I didn't quite get to molarity and some of the other stuff. But one of the things from Unit 3 that comes into Unit 4 is that idea of molarity, and can you change molarity to moles? So it basically says you want to make 2 liters of a 0.1 molar potassium iodate solution. So keep in mind, they're giving you the formula. So this is not something you need to worry about. Also keep in mind, they're giving you the molecular weight. So they're giving you the molar mass. And this one you should be able to do without a calculator. So take a stab at it without a calculator. Notice that the molarity is 0.1. So you really should be able to multiply things by 0.1 in your head or on paper without a calculator. We call that mental math. And that's definitely a skill I need y'all to be comfortable with. So if that's something you need to work on in the time between now and May, kind of make a note of you need to do some more mental math type problems. So I've got 8 answers so far. The other thing I want you to notice is the questions are set up to where the answer is either 42.8 or 21.4. So really the first thing you need to do is the math. And once you do the math, then you can kind of go, okay, now which one of the 42.8 or which one of the 21.4 comes into it? Now, it may have been a while since you guys have made a solution because this year in COVID, I know, but you still need to do the basics of how to make a solution. Oftentimes on the AP exam, they'll say, okay, what labware do you need, right? So you wouldn't make a solution in a beaker. It's not precise enough. Maybe you make it in a volumetric flask or those kinds of things. So those are the little things that you can really get lots of points on. So just kind of make a note of, I need to work on this, or in May, I need to go back and look at how do you make a solution. So let's see what y'all's responses are. I got a lot of B's, an E, an A, so a little bit of everything. So let's actually go ahead and see how you work this problem. So it's 2 liters. And remember that 0.1 molar, molarity means moles per liter. So if I set up the math, it's 2 liters times 0.1 molar times the molar mass, which is 214, is equal to 42.8 grams. You can also think through it and go, oh, wait, it's 1/10 of a mole. 1/10 of a mole is 21.4 grams. And that's how you would make 1 liter of solution. But I want to make 2 liters of solution, so I can just double it. So you can either set it up dimensional analysis, or you can actually sit down and do it like in your head, where you kind of go, it's 0.1 times masses times liters kind of thing. But which one of the 42.8 is correct? So 42.8 and add 2 kilograms of water, 42.8 and add 2 liters of water, or 42.8 and add water until it has a volume of 2 liters. And remember, whenever you're making a solution, it's not that many moles per liter of water, it's per liter of solution. So for example, if you chose B, if you chose D as in dog, the problem is if you added 2 liters of water and then you added 42.8 grams of solid, that would make the volume go up. So even though it was 2 liters of water, when you added the solid to it, it would go up, and now it wouldn't be 2 liters. So the correct answer is you add the solid, you add some water, you shake it up, and then you bring the volume up to 2 liters. So the answer is always that you add enough water to make it a total of 2 liters. All right, so here's another type question that you might see. This is a particulate drawing question. This one you get to draw on. So I gave you a chemical equation, and what I want you to do is circle the one that you think is the correct representation for this particular equation. So for the whole equation, which drawing is the best one. And you can just circle it or box it or something like that. Oftentimes on the AP exam, they're going to ask you to do that. Circle the correct one or something like that. And if you ever make a mistake and you're like, oh, I circled the wrong one, what do? You put an X through it, and then you circle the one you want to circle. And AP readers know that if you cross something out or if you put an X through it, that they are not to read that as part of the answer, right? So even if you make a mistake, it's okay. All right, so let's see what some of y'all's responses are. Okay, they not only circled the right one, they put a bunch of X's. There's a circled one. The other way to think about this is you can totally get rid of the ones that aren't right. And I appreciate that so many of y'all are doing that, crossing out the ones you know aren't right, because oftentimes it'll be like, 4 or 5 choices, and then you just need to figure out what ain't the answer. That's a perfectly reasonable way to take the AP exam. And that's a lot. That's a lot, y'all. Some of y'all's drawings, very, very busy. All right. So the first one right here, where there's no precipitate, that's definitely out because it shows in the equation a solid is being made. The problem with the bottom right one is, it says solid lead nitrate, but lead nitrate in the equation, that, lead nitrate solid at the bottom is not the precipitate that's being made. So the idea is we want to show that the correct precipitate is being made, the PbI2. Right? We know that the sodium and the nitrate are aqueous, that they're going to be spectator ions. They were on the left-hand side of the equation. They didn't take part in any part of the equation. So this particular drawing on the lower right is not right because it has sodium ions, but it definitely doesn't have any nitrate ions. Right? So the one at the top right is wrong, in that it has the right precipitate, but the problem is it still has iodide ions left over. And so you might be thinking, wait, I thought the iodide ion was supposed to precipitate out. So the one that's the best one is that top middle one, because it's got the sodium and the nitrate ions. They show as ions, and it's also got them as spectators and the solid sitting on the bottom. Right? So another way that they'll sometimes do this is they'll say, hey, here's a water molecule. It looks like a Mickey Mouse. Here's the lithium chloride crystal, right? So then they give you a space, and you'll get to draw in just a second. They want you to show the interactions by making a drawing that represents the different particles. Now, your job here is not to speed read through the directions. Your job here is to make sure you understand what they want on the AP exam. I'd hate for you to miss a point on the AP exam because you didn't read. So it says only include 1 formula unit of LiCl and no more than 10 molecules of water. So don't go drawing 100 molecules of water and a bunch of LiCls, right? But your drawing must have the identity. So you're gonna have to label things, and it has to have a charge, but everything must be in the correct orientation. So water molecules look like that. Lithium chloride crystals look like that, right? And so we're going to let y'all draw in this space. So you can draw your very own solution. So keep in mind, you need to have no more than 10 water molecules and 1 representative unit of lithium chloride. That means 1 lithium ion and 1 chloride ion. And they must be labeled, and they must be in the right orientation. And if you haven't done a lot of that this year with your teacher, make a note and say, hey, can we practice drawing some representative particulate drawings or particulate drawings or drawing ions in solution? A lot of times that comes in on the FRQ portion of the AP exam. Sometimes they make you pick it in the multiple choice, but oftentimes they're asking you to draw. All right, so this time I'm going to scroll down to the very bottom. War Eagle, no, that's automatically wrong. So, oh, look at that beautiful water molecule that somebody deleted. So it's lithium chloride. So you shouldn't have an F in there, whoever has that. So there's a lithium and there's the chlorine. So coming along. I know it's hard to draw, especially with a mouse. I like all the different colors. Ooh, it's a lot of yellow. Okay, so this person that I'm sharing with you, they actually drew them in different colors and showed them that. So if y'all are looking at my shared screen real quick, if you could flip over to that, I want to point out something, what's good and bad about this particular drawing. And again, we do this to figure out what we're good at and where things get better and those kinds of things. So the problem with this one particular drawing that I'm showing you is it does say that the little green dot is lithium. However, one of the directions said to indicate charge. So you would have to have a charge on the lithium and a charge on the chlorine. They did pick the right size though. Lithium is smaller and chlorine is bigger. And we get that from those periodic trends that we talked about in Unit 1, right? So thank you for labeling them. You also could have labeled it off to the side, person who drew this, right? You could have put Li plus and Cl minus over in your diagram over off to the side. But also notice they've taken the time to orient the water molecules. So water molecules are polar. We talked about that last time. And so the hydrogens would turn towards the negative ion, and the oxygen, the blue part, would turn towards the positive ion. So you're looking for a couple things here. And what I want you to think is, did I do this, okay? So here's a lithium in the shared screen. Here's a lithium with the oxygens touching it. So first of all, this is a lithium chloride solution. So the first thing you have to have in your drawing is the lithium is separated from the chloride, right? They exist as two different ions kind of swimming around solution. That would be first. The second thing is you have to show them as ions. So did you put a charge for each one? The third thing is, are the small and chlorine is large? Very important. And then the last thing is are the water molecules oriented in the correct orientation? So you have to make sure all the water molecules, if you draw a lot of them, you have to make sure that they're all facing the same direction. Because if you have one water molecule facing the right direction and one water molecule not facing the right direction, then the AP reader was like, maybe they know what they're talking about. But when you prove yourself wrong, we can't give you the point, right? So these are some pretty good answers, right? So you can do particulate drawings of solutions, and that's a good thing. I just wanted to remind you of something from Unit 3. It was called Beer's Law. Beer's Law is the more concentrated a solution is, the darker it is. So the idea is we can take something like potassium permanganate, which is very, very purple, and we can slap it in something called a spectrophotometer, and we can take a reading of the absorbance. And notice that as the concentration goes up on the graph, that the absorbance goes up. So if we take 4 standards or known concentrations and their absorbance, oftentimes the AP exam will say, okay, let's see what they know about spectroscopy. If the absorbance is this black line for the unknown, then all you have to do is go, oh, I have to figure out what is the X coordinate or the concentration of that unknown. So if you haven't ever seen that before, ask your teacher, hey, can we look at some Beer's law? It's called the Beer-Lambert's law of concentration. And because if you've never seen one of those on the AP exam, then you're probably going to miss it. And that's a really easy way to get points. All right, and the last thing from Unit 3 before we move on to Unit 4 is which one of those would be the best technique for recovering solid potassium nitrate? So you drag the icon to what you think is the correct answer. Which one of those is the correct way to get solid potassium nitrate from a solution of potassium nitrate? All right, y'all are coming right along. All right, let's see. All right, so a lot of moving around, that's good. Okay, so let's talk about why all the wrong ones are wrong. So paper chromatography is where you take a piece of paper that looks like a coffee filter or something, ink on it. Ink is made up of several different colors of stuff that are all together. So paper chromatography is you put a drop of something on there, you dip it into some kind of solvent, and as the solvent moves up the paper, it pulls things apart. And that's not going to work for potassium nitrate because potassium nitrate isn't a mixture of things. It is just one thing. Filtration is when you pour it through a piece of filter paper and the filter paper catches the solid. So the problem here is that will only catch precipitates. It won't catch aqueous solutions. So as part of the AP thing, you should know a very small set of solubility rules. So sodium and potassium things are always soluble when they're dissolved in water, and all nitrates are soluble. So potassium nitrate is, of course, going to be soluble. So it would not get caught in a piece of filter paper. It would just go right through because it's dissolved. Titration is you use a known to calculate the concentration of an unknown. So some of y'all may have done a redox titration where you titrate potassium permanganate with something like oxalic acid or something like hydrogen peroxide. And the idea is you're using a known to figure out the concentration of an unknown. And for those of you who are in acids and bases now, you're learning how to do acid-base titrations. Electrolysis is using electricity to split things apart. And that's not something we want to do. We don't want to separate the potassium from the nitrate. We want to actually get it together. So how do we get rid of all the water? You just evaporate it. So you could either let it sit out for a long time or you could put it on like a hot plate, but let the water go away. And what you would be left with is just the potassium nitrate. All right, so anytime you're doing stoichiometry, these are your choices. So you can be given grams and you have to find grams. That's one choice. You can be given moles and have to find moles. You can be given liters of gas and find liters of gas. And in Unit 3, you talked about the PERV-NERT, or PV equals nRT, the ideal gas law. That N represents the number of moles. And then finally on the bottom, molarity is moles per liter. And so moles per liter, if you're given molarity and volume, then you can find moles. But realize that all of the calculations have to go through the balanced equation. So what I tell my students is this: if you don't have moles, find moles. In fact, when in doubt, mole it out. If you're given grams of something and you don't quite know what to do, change it to moles. And then you use of what you're given to moles of what you're looking for. And then finally, you go to look, if you want to find grams, use molar mass. If you want to find a solution, then use that molarity equation, right? But stoichiometry is always on the AP exam, and that's a skill that you probably learned in Chemistry 1, and I just want you to make sure you have that skill with you for the AP exam. So here's the type of problem you might see. And this one is kind of over the top. So we're not going to actually have y'all do it. But the first thing we need to do is write the equation for it, right? So barium nitrate, aqueous, is added to potassium carbonate, aqueous. And I know that because it says both of them are solutions, right? And it says barium carbonate, which when you look at BaCO3, I want you to notice it looks like bacon. It says it precipitates. And again, that potassium nitrate is going to be AQ, right? So the first goal is to write that balanced equation. The second goal is to go ahead and do some math with it. So I need to, if I'm not given moles, let's find moles. So it tells me that I've got 0.02 liters. Remember, when you're doing molarity, it's got to be in liters. And I'm finding the number of moles of K2CO3 in that first part. And then I'm looking at that balanced equation I just showed you. And it's a 1-to-1 relationship, which the K2CO3, I'm going to precipitate out 0.004 moles of barium carbonate. The next thing is, how many moles of barium nitrate did I have to begin with, right? So if you had 0.03 liters and 0.4 moles, then what I can do is I can calculate to start with. So when it asks you for what is the concentration after the reaction, you have to think about, well, how much did moles of barium stuff? How much reacted? That was the top calculation. That was the top calculation. And then when you do the math, you can figure out how many moles are left over. And then once you have the moles left over, it becomes a simple thing of take the moles that are left over and divide it by the total volume, because you have to remember you had 20 milliliters and you added another 30 milliliters. So that's 50 milliliters total. So the idea is take barium ion in solution and divide it by the total volume. That's a really hard stoichiometry type question, right? But it still holds true. If you don't have moles, find moles, figure out what you're looking for, how much you start. We're still in moles. Use that moles divided by liters to find the molarity, which is what they want, the concentration. All right. So it says when the equation above is balanced and all coefficients are reduced to the lowest whole number terms, what's the coefficient for O2? So if you guys could go ahead and balance this equation like you know how to balance equations, but make sure that you're picking just the coefficient for O2. So go ahead and take the time to balance this equation. This is something you'd be expected to do on the AP exam. While you guys are working, I'm going to go ahead and talk about what is the exam like. This is an older question. Now there's only 4 choices instead of 5. But sometimes if you get to a question like this, like let's say that balancing equations is not your best thing, you want to make sure you see every single question. So sometimes it's totally okay to go, I'm going to skip this question and come back to it. I don't want you to run out of time. So just stick with what you're doing and keep plugging away at it and make sure you see all the questions, because you may actually know the last 3, right? You're like, oh man, I would have missed them if I had stuck on that one question for 5 minutes. Guessing anyway, then just save that question for the end and you can guess at the end. So I've got 18 responses so far. Let's give you all another minute and we'll see. And then I'll kind of give y'all some hint like how would I solve this kind of problem. Mr. Pope points out that a rice table makes that previous problem that we did about barium very, very helpful. If you've been taught the rice table technique, then yes, that's true. It takes a little bit longer, but a rice table technique can be very helpful. However, if you didn't learn the rice table technique, then you can ask your teacher to show it to you, or just look up an ice or rice table video on YouTube, kind of a thing. There are lots of different ways to do stoichiometry, but I'm trying not to give you like, oh, my teacher didn't teach this because she doesn't know or he doesn't know what they're doing. Well, just lots of different ways to do it. So if you don't understand something, then you know. All right, so let's see. You got 37 responses, and y'all are saying C by and large. Okay, so far so good. Man, I hope C is the right answer. So this is how I would have actually done this question. I would have started by balancing everything except the oxygen. So I got 10 carbons on the left. I got 10 carbons on the right. I got 12 hydrogens on the left. I got 12 hydrogens on the right. I got 1 sulfur on the left. I got 1 sulfur on the right. So I would have done that first and got everything except oxygen. Anytime you have oxygen or something that's all over the place, it always needs to wait till the end. And then I would just total up how many oxygens I have on the right-hand side. So there's 20 total in the carbon dioxide. There's 2 in the SO2, so that's 22. And there's 6 in the water, so that's 28 total. There's 4 oxygens in the great big C10 molecule, which means I need to come up with 24 more oxygens. And that's how I decided to put that 12 in front of there. Right? So remember, every multiple choice question counts the same, and there is no penalty for guessing. So if you got stuck and you're like, oh, it's going to take me a really long time, skip it and come back to it later. All right. Now, this is a titration question. So this is kind of I'm going to let y'all work through this. Go ahead and do the math. I gave you the balanced equation. If you don't quite know where to start, you're starting with the permanganate. So go from milliliters and molarity of the MnO4. And what you're looking for is the concentration of the iron. Some of y'all may have done a permanganate redox titration. And there were also some titrations like this that you can do virtually. So maybe you've seen this done before. You may have done the science and motion one. Yeah, if I got the 30 instead of the 28, then I apologize, but I thought I got that math right. So, Mr. Poe, can you kind of back check me on that last equation? I think I got that right. I'll go back to it in just a minute. So again, you'd have about a minute and a half to answer this question on the AP exam. So if you know it's going to take you more than a minute and a half, then a good test taking strategy is skip that question, come back later. All right, I got 15 answers so far. All right, so I'll give you all like another 30 seconds, so take a stab. All right, so let's see what y'all are saying the answer is. It's kind of split evenly between B and C. So it's kind of an even race. So we'll see what everybody says. Couple E's that just went up, so maybe that is. All right, so let's talk about how would you actually go solve this problem. So you'd want to start with go from milliliters to liters, so 0.014 liters, and times the molarity, because remember that molarity times volume is equal to moles. So that first step, what I'm doing is I'm changing it to moles of MnO4. And then I'm using my balanced equation to go from moles of MnO4 to moles of Fe2. So there's a 5 in front of the Fe in the balanced equation. There's a 1 in front of the permanganate in the balanced equation. So that's where I got that step. And that tells me how many moles of iron there were. So again, this is titration. We're using the known permanganate to figure out the unknown, the iron. So once we have the moles of the iron, we just divide it by the volume of the iron. Because remember, molarity is moles divided by liters. So in the problem, it told me it was 25 milliliters. And so when I do that math, I get 0.14 molarity of the iron ion. So the correct answer there would have been E. Right? And again, if you didn't quite understand this, remember that this will be posted out to YouTube, and you can always bring this up to your teacher and say, hey, can you kind of go through this with me? I don't understand where I missed it. Obviously, if y'all have questions, feel free to type them in the chat box because I'm watching that as well. All right, the other thing you have to be able to do is identify a conjugate acid-base pair. So those of you who are doing acids and bases right now, this is probably old hat, but you actually learned it for the first time back in Unit 4, where it was chemical reactions. So what is the conjugate acid of NH2 minus? What that means is NH2 minus is a base. So what would be the conjugate acid of NH2 minus? And if you know what you're doing so far as identifying those pairs, this is really a question that you can pick up on time because there's no math involved. So if you can answer this question in 15 or 20 seconds, then you've got a whole nother minute that you can spend on another question. All right, so we're up to 35 responses. Let's say what y'all are saying. All right, B. Okay, a lot of B's. No E's, that's good. All right, so what is a base? A base is anything that absorbs hydrogens, right? So if NH2 is a base and it's absorbing hydrogens, then the conjugate acid, the thing it becomes, would be something that can give away H's, because after all, that's what acids do, is they give away H's. So if NH2 is a base, then what would it become when it absorbed an H? And the correct answer there is B, right? So NH2 minus absorbs an H and becomes NH3. That is the conjugate acid. And the NH3 could give up an H and turn back in NH2 minus. That's why we call it a conjugate acid. EP Oxford, how do you know it's a base? Well, conjugate acids always occur in pairs, right? So you would have a conjugate acid-base pair. So one thing is an acid, one thing is a base. So if they're telling you, tell me what the acid is, then it implies that the NH2 is acting as a base. All right. So the other way to ask a stoichiometry problem beyond doing a lot of math is these particulate drawings. Now, in this particular one, they gave you choices about how many molecules and that kind of thing. But this would be a lot of things to draw in one sitting, right? There's a lot of stuff going in on that box on the right. So just tell me how many D, and that would be the large gray circle, and how many F2 molecules should there be in the left box, and you get to just type out your answer. Okay, I got 21 so far. And they also could have asked you write the balanced equation, which would be D plus 2 F2s makes DF4. They could ask you to do that. They could ask you what's the limiting reactant and what's the excess reactant. So there's lots of things that they can do with a picture like this. And obviously you can look and go, oh, there's no more D molecules left all by themselves. So D must be limiting. And there are some F2 molecules hanging around all by themselves on the right-hand side, which means it must have been an excess, right? So there's lots of questions that you can actually write about this. I'm just going to peek at some of your responses real quick. 10 and 25, 10 and 26, 10 and 25, 10 and 25, 10 and 50. Scroll down. 10 and 48, 10 and 25. Where am I? I don't know. Somewhere in Alabama. 10 and 22. And I know some of y'all hurried. So if you get it wrong, it's okay, as long as you're in the right ballpark. Some of y'all are saying 50 and 10 and 50. All right. 500 D left. Okay. I don't think you meant 500. All right. So this is how you would come about to and work in this problem, right? There are 10 DF4 molecules on the right-hand side. Add them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which means there had to be 10 D molecules on the left-hand side. So you'd have 10 Ds on the left-hand side. And then there are 10 fluorines attached to each DF4, right? There are 4 fluorines attached to each DF4. So 10 times 4 is, there's 40 of them over there. Plus you have another 5 in there of F2 molecules. That means there's a total of 50 F atoms. But keep in mind that fluorine would be diatomic. So the correct answer there would be not 10 and 50, but 10 and 25. And the tricky part there was it's F2s, right? So you got to, yeah, there's 50 F atoms, but you're going, oh, they're diatomic, so I got to cut that number in half. All right, this looks like I can't type. Now, this is a gas type question, right? So it's got 0.2 moles of SO2 and 0.2 moles, wow. I typed this, I did, but my O's became, my zeros became O's, so my apologies. You've got 0.2 moles of SO2 and 0.2 moles of O2 in a 4-liter flask. What is the pressure in the flask? So they're starting you off with moles, and I'll give you a hint. one of these things is limiting and one of them is in excess. So you need to figure out which one is limiting. And then you need to figure out how much of the excess is in excess. So they're starting you with moles. So just go to the balanced equation. And then at the end, they're asking you for the pressure in atmospheres. And remember, when you have moles and you're looking to do stoichiometry to pressure, you're really looking to use that PV equals nRT formula. If you don't know the R value off the top of your head, it's 0.08206, or it's also on the reference sheet. There's no reason for you to memorize that because those things will be given to you on the reference sheet. Now, on the AP exam, if this was an FRQ, then they would expect you to show all your work. So you'd want to make sure you label things as you went. You'd want to make sure that you're showing your mathematical steps. Make sure that you're plugging things correctly into the gas laws, because oftentimes they will give you points along the way for doing a good job of showing your work and showing that you know something about the process, even if ultimately you don't get the right final answer. Okay, I'm just going to peek at your responses real quick. Okay, somebody got a 50, got a 60. The rest of y'all are in that between 0 and 3 kind of a thing. All right, so let me go ahead because we want to make sure we honor the time. And I'm just trying to give you all a taste of what kinds of problems might you see kind of a thing. So this was my attack, how I worked the problem. So the way I was taught to do limiting reactant is I go from each number given to me in the problem and I find the amount of product. So I took my 0.2 moles of SO2 and I took my 0.2 moles of O2 and I found out how many moles of SO3 each number would make. And then I know that the smaller answer, the 0.2 moles of SO3, is my limiting reactant. Therefore, the SO2, the thing that decides how much product gets made, is my limiting reactant. So that means my O2 is going to be my excess reactant. So my next step would be when I use up my moles of SO2, how many moles of O2, that's right there in the middle, go from moles of SO2 to moles of O2, again, using my balanced equation. And that will give me that I've got 0.1 mole of oxygen used up during the chemical reaction. I know I started with 0.2 moles of O2, and I used up 0.1 moles of O2. And then that would leave me with 0.1 moles of O2 left over. That means I made 0.2 moles of the SO3, and there was a 0.1 mole left over, which means I have a total of 0.3 moles of gas when the reaction is complete. KP, how do I know which one's the limiting reactant? If I work each problem going from moles of reactant to moles of the product, then you have to pick whichever one gives you the least amount of product. That's how I knew which one was limiting. So once I figured out that it's 0.3 moles of gas, all I'm going to do is plug that into PV equals nRT. And that's exactly what I've done there at the bottom. It's the number of moles, 0.3, times the R value, times the temperature. Now remember, temperature has to be in Kelvin in gas laws. So you had to change 25 to 298. And you do that by adding 273. and then you divide it by the volume, the number of liters, and I get the answer 1.8 atmospheres. So most of y'all were pretty right on. That was good. So that's a stoichiometry problem where they're asking you like a gas law thing. So this is about oxidation numbers, right? So it's been a while since you had oxidation numbers. So let's see how well you do, right? So kind of look over the question and see if you can figure out which one is the right answer. Now, if you want to get rid of certain wrong answers, of course you can do that, but you're just going to drag the icon to the one that you think is the right answer. So go ahead and read each answer choice. And I'll tell you right now, it's not E, because a disproportionation reaction is not a word they ever say in AP. So just don't even worry about it. It's a fancy, it sounds fancy, like that could be the answer, but that's not it. So let's see where y'all are putting the icon. Okay, some of y'all are doing D. A couple of y'all are doing A. Several B's. Okay. So let's go through why each wrong answer is wrong. So the correct answer is D as in dog. A, the oxidation number of oxygen does not change. Well, on the left-hand side, oxygen is paired up with fluorine. So it's going to have an oxidation state of +1, because fluorine always gets to be -1. Normally, oxygen's -2 when it's combined with something else, but fluorine always gets to be -1. On the right-hand side, oxygen is 0 because it's an element all by itself. And then letter B is wrong because hydrogen is a +1 on the left-hand side, and hydrogen is still a +1 on the right-hand side. So B is not right. C is wrong because fluorine always gets to be -1 unless it's all by itself. Then it would be an element in its standard state, and the oxidation state would be 0. So if you found yourself not remembering this very well, then you definitely need to scribble down somewhere, hey, I need to go back over and relearn my rules of assigning oxidation numbers. You'll see oxidation numbers again a little bit when you get to Unit 9 for electrochem, but this is if you know your rules of assigning oxidation states, then this would be a very easy point for you to get on the AP exam. How do you know which oxidation number goes with which? So I'll just take you through it real quick. H2SE, hydrogen always gets to be +1. So 2 hydrogens means it's a total of +2, and they have to add up to be 0. So that means Se has to be -2. In the O2F2, F is always a -1. There's 2 of them, which is a total of -2. Which means each oxygen has to be a +1. The SEF6, if the fluorine is a -1, there's 6 of them is a total of -6, then selenium has to put up an oxidation state of +6 because I kind of have to cancel out. The HF, F is a -1, H is a +1, that one's easy. And then any element all by itself in the standard state, which is oxygen here, gets an oxidation state of 0. And remember that an oxidation state really just tells you has something lost electrons or has something gained electrons. And obviously, you can always ask your teacher, hey, can you go back over that one more time? Or look for a video. All right, so this is all about assigning acid base pairs, right? So we talked about before, what's an acid base pair? So you got an acid and a conjugate base, and you've got a base and a conjugate acid. So when I say which species act as bases, then I'm asking both a base and a conjugate base, right? So there should be one of them on the left-hand side of the equation and one of them on the right-hand side of the equation that is acting as a base. So go ahead and draw, you can underline it or draw something next to it or something like that. For the species, see how it's plural, right? So the act as bases. So you want to say there's two of those answers that are acting as bases. You guys are doing so well. All right, so let's see. So somebody said 2 and 3. Somebody else said 2 and 3. Somebody else said 2 and 3. 2 and 3 seems to be a very common thing, and a flower that was lovely. So how do you know what a base is? A base, remember, is something that absorbs hydrogens. So is the HSO4 absorbing hydrogens? No, the HSO4 actually loses a hydrogen when it goes from the left to the right. So in that case, the HSO4 is actually losing a hydrogen. It's acting as an acid. So who's gaining the hydrogen? That would be the water molecule. So the water molecule is actually gaining a hydrogen and turning into H3O. So the H2O would be the base, and the H3O plus on the right-hand side would be its conjugate acid. The HSO4 is the acid, and the SO4 on the right-hand side would be the conjugate base, because that SO4 2- could absorb another hydrogen acting as a base and turn back into HSO4. So this is kind of a, do you know your definitions? All right, so which one shows that something is being reduced? So oxidation is when you lose electrons. So LEO, Leo says GER. So LEO, losing electrons is oxidation. Leo says GER, GER, gaining electrons is reduction. So which one is being reduced? Which one is gaining electrons? Just drag the icon for the one that you think is gaining electrons. So gaining electrons means that you're going to be, your oxidation state is going to become more negative. So you can get rid of any of the ones that are becoming more positive because you're gaining electrons. So let's see what y'all are putting for icons. Okay, most of y'all seem to be centering around D and E. Okay. So if we look at the first one, the oxidation state of just calcium is 0. It's an element in its standard state, and it's becoming a 2+. So that's actually being oxidized because it's becoming more positive. Same thing is true for B. Hg is 0, and Hg2 with a 2+ has an oxidation state of +1. So it's also becoming more positive. The Fe2+ going to Fe3+, that's also becoming more positive. And so you're left with D and E. So the oxidation state of N in nitrate, NO3, is a +5. And the oxidation state of the nitrogen on the right-hand side is a +2. So NO, oxygen is -2, which means the N is +2. So the nitrate on the left is going from a +5 on the left to a +2 on the right, which means it's being reduced because you're getting more negative. On the right-hand side, letter E, you're going from a +4 state on the left-hand side for sulfur to a +6 state on the right-hand side for sulfur. So in the SO3, it's a +4 state. And on the right-hand side, SO4, it's a +60. So you might want to go back through and research, how do I assign oxidation numbers again? It's been a while. Right, so here's another type of question that they sometimes ask, right? So I'm not actually going to have y'all draw this one, but they say equal masses have reacted. And you're like, wait, what do I do? They didn't give me a number. So this is what you do when they don't give you a number. When they say equal masses, pick a number. So pick a number like 35. So you would work a problem going from 35 grams of K to grams of KCl, the product, remember? And you work a problem from 35 grams of chlorine to grams of KCl, the same product, right? And then whichever number gave you the least amount of product is limiting. And the limiting reactant means that one is used up. So if K is limiting, there will be Cl left over, Cl2, and all the K will be used up. If Cl was limiting, if the Cl2 was limiting, then there would be no Cl left. There would be some K left. And it doesn't matter which one you do, there would be some KCl made. So there'd be some products and some leftovers of one of the reactants. So when they say equal masses and you don't know what number to pick, I usually just pick any number. It doesn't matter. All right, so this is a very common question for the AP exam. So here's what I want you to think about. When they tell you it's 0.1 moles of NaCl and 0.1 moles of CaCl2, they're trying to play a trick on you. So they're saying to precipitate it out with silver, how many moles of silver will you need? Well, the number of moles of silver that you need is equal to the number of moles of Cl ion. So think about what is the total number of moles of Cl ion running around in solution, and then go ahead and choose an option. Okay, a few C's, a couple D's, and no E's. So here's what I want you to think about. 0.1 moles of NaCl will give off the same number of moles of Cl ion, because for every one NaCl, there's one Cl. So 0.1 moles of NaCl will give off 0.1 moles of Cl. 0.1 moles of CaCl2, for every one CaCl2, there's two chloride ions. So the total number of moles of chloride from that would not be 0.1, it would be 0.2. It's like saying there's 47 people on the Zoom call, how many eyes are there? 47. How many ears are there? Well, assuming everybody has, sorry, that was wrong. Hang on, back up, try it again. If there are 47 people in the room, how many noses are there? 47. How many eyes are there? Well, each person has 2 eyes, so I would have to multiply that 47 by 2. That's what you're doing here, and the correct answer ends up being C, just because there's 0.1 moles from the sodium and 0.2 moles from the CaCl2, which means there's a total of 0.3 moles of chloride ion out there in solution. So you would have to add the same number of moles of silver. My bad. All right, we're going to skip this. Right. A very common thing on the AP exam, this is both stoichiometry and redox, is they want to know how many moles of electrons are transferred. So you would have to figure it out just either by the BR or by the MN. right? So you'd have to assign oxidation states and figure out how many moles of electrons are transferred. So if you were doing the oxidation state of Mn in MnO4, it has an oxidation state of +7. And on the right-hand side, the manganese has an oxidation state of +2. And that means that each permanganate is gaining 5 electrons. And since there are 2 manganeses, then that means there's a total of 10 electrons. That's one way to do it. You also could have looked at the bromide, and bromide on the left-hand side, the Br minus, has an oxidation state of -1. And bromine on the right-hand side is its element, and so it would just have an oxidation state of 0. And so you've got 10 things going from a -1 to a 0. So whichever one you picked, that's how you would figure out how many moles of electrons there were. All right, now this is a yes or no thing, right? Does the following diagram make sense? Yes or no? No, yes, no, 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 because yes, no, yes, yes, no swag, yes. Okay. So, and then if not, why not? So that was good that y'all were typing things out. I just want to make sure we finish on time. So I know I'm over now, but I'm trying to finish in a minimum amount of time. The thing that bothers me about this one, the correct answer is no. And the correct answer is no, because we know that hydrogen and oxygen are diatomic. So there should not be individual little tiny circles running around. They should be in pairs, right? Other than that, the thing looks okay. But if you looked at the number of tiny little circles on the left, they don't match up to the same number of tiny little circles on the right. So tiny little circles on the left is only 6. And tiny little circles stuck on the water molecule, there's actually 12 of them. So that would be a no for me. So let's look at the other choices. Is this one any better? Yes or no? And if not, why not? No. Yes. No. Yes. Yes. Okay. So a lot of y'all are saying yes and no for really good reasons. So this is still a no because they're not diatomic. So you'd want the oxygens on the left-hand side to be stuck together, and you want the hydrogens to be stuck together. But the ratio is right. This time there's 6 oxygens and 12 hydrogens. So this time they got the ratio right. What about this one? Yes, yes. It seems good, but right. So remember, oxygen should be diatomic. Oxygen is one of those diatomic elements. Perfect. Thank you. I drew it myself. Not really. I don't know what twice means. Right. So this one is actually pretty good because it's got the right number of elements, right? So there's 6 total larger black dots, and there are 12 total smaller dots representing the hydrogen. And that fits the ratio and their diatomic. So this one looks pretty good. What about that one? Does this one look any better? And this is the College Board's way of giving you a math problem on the multiple choice without actually asking you to use a calculator or do math. So can you match up these particulate drawings? Let's see what y'all are saying for answers. No, 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 no. Hi, I'm Benjamin. Thank you. No, no. Okay. So the hydrogen is diatomic on the left-hand side. That's okay. So there are two little things stuck together. That's fine. But the oxygens are off. If you look, add up the total number of big black circles, and you get 2, 4, 6, 8, 10, 12. You get 12 oxygens. Yet over on the right-hand side, there's only 6 oxygens, right? So there's only 6 oxygen atoms, and there's a total of 12 oxygen atoms on the left. So this would not be an acceptable answer. So let's see if you're any better at identifying conjugate acid-base pairs by dragging the red dot to the acid and the blue square to the base. It can be any acid. It can be the acid or the conjugate acid. It can be any base, but it should be, they come in pairs. So you'll have the red thing on one side of the equation, the blue thing on the other. Let's see what y'all are putting. You're going a little bit of everywhere. That's good, but you'd have to have a red thing on one side of the equation, the blue thing on the other, because they occur in pairs, right? So the correct answer, let me show you what the rubric was. You get 1 point for saying that the CH3CH2COOH is the acid, and then its conjugate, the thing on the right-hand side, was when it had lost a hydrogen, right? Or you could have pointed out that H3O is the acid and the H2O is a base. So if you went back, the H2O absorbs a hydrogen, so it's acting as a base, and the H3O is what it turns into, the conjugate acid. Or you could have said this big long honking molecule is an acid because it loses an H, and the thing it turns into on the right-hand side is a conjugate base. So vocabulary, very, very important. On the AP exam, they're not going to ask you to drag red and blue things, but you got to identify. Right. So the last thing I want to do is this balanced net ionic equation. So let's see if you guys can write a net ionic equation for the reaction between solid lithium and water to make hydrogen gas and lithium hydroxide. And lithium hydroxide would be aqueous. The lithium hydroxide would be aqueous. And this will be the last thing we do. So as y'all are working, I'll go ahead and point out a couple of the things that I thought you guys might want to go back and look at. It's been a while for most of y'all since you saw this, but knowing oxidation states and assigning oxidation numbers, very important. You can go back and do that. Finding moles using molar mass or finding moles using molarity. A couple of y'all struggled with that. And then finally, that acid-base pair thing. When you get to acids and bases, you might want to look through that again. But notice I didn't ever say the answer was tonight Coulomb's law, because for tonight at least it's not. So let's see what some of y'all's answers are. All right, so y'all are a little bit of everywhere. So let's go over how you do this, right? So when you write a net ionic, here's what you do. Write the balanced equation. So that's what I did. So lithium combines with water to make hydrogen gas and lithium hydroxide. And that's aqueous. I told y'all it was aqueous. So then what's the rule? How do you know when you make a net ionic, how do you know what to do? We'll take anything that's aqueous or anything that's a strong acid and pull it apart into its ions and then see if there are any spectators. Spectators are ions that are the same on the left and the right. So I pulled apart the lithium hydroxide ions because lithium hydroxide is aqueous. So that bottom equation that you're seeing there in blue, that is the net ionic equation. That just happens to be one where we didn't get to cancel out any spectator ions, right? You wouldn't pull the water apart because it doesn't pull apart. You would leave the lithium as is because it's a solid. You would leave the hydrogen as a gas because it's not dissolved in anything. It's not like you're going to pull it apart into ions. So knowing net ionics is also very important. Thank you guys so much for coming out tonight and sticking with me for an hour and 15 minutes. I'll be on here for another minute. If you guys have to ask any questions, I'll be happy to answer them. You are more than welcome. I'll see y'all back. And we won't have one next week because we're doing regular review sessions. So I will see y'all in 2 weeks. So.